Welcome to this next video in the playlist on group theory. In this video, what we're going to do is introduce a whole new family of groups, namely the alternating groups on the set of n elements. Okay, and these are going to be subgroups of the symmetric groups on the set of n elements. So we have studied in previous videos in this playlist on group theory the symmetric groups on the set of n elements. What we're going to define in this video is what will be denoted a subscript n, known as the alternating group on the set of n elements, and this is going to be a subgroup of the symmetric group on the set of n elements. Okay, now really to define this, we're not going to be interested in the case where n is equal to 1, so we'll want n to be greater than or equal to 2. So for the symmetric group on the set of n elements where n is greater than or equal to 2, we can define a subgroup of this which is going to be the alternating group on the set of n elements, and that's what this entire video is going to be about. Okay, so how are we going to do this? Well, we're going to have to develop some theory concerning the symmetric group on the set of n elements firstly, in order to actually define the alternating group on the set of n elements. What we need to understand is that every permutation in the symmetric group on the set of n elements can actually be ascribed a number that is called its sign, and this number is either going to be +1 or -1. Okay, so every permutation I claim, and we'll understand this later on, every permutation in the symmetric group on the set of n elements can be given a sign which will be the number +1 or -1. And the alternating group on the set of n elements is going to be the subgroup of all the elements of the symmetric group on the set of n elements that have positive sign, +1 sign, rather than -1. So chuck out all of the elements of sign -1, keep all of the elements of sign +1, and that then is going to be the alternating group on the set of n elements. Okay. So, to understand this, the first thing we need to understand is that any permutation of the set of n elements in the symmetric group on the set of n elements can be decomposed into a succession of transpositions. That concept is absolutely key to understanding the sign of a permutation in the symmetric group on the set of n elements. But before we actually discuss that any further, let me firstly just remind you of the fact that any set permutation in the symmetric group on the set of n elements can be decomposed into a cycle decomposition. That fact will be extremely important when we want to discuss why it's true that any set permutation can be decomposed into a succession of transpositions. Okay, so I'm just going to remind you of the concept of the cycle decomposition of a set permutation of the set of n elements that is in the symmetric group on the set of n elements. Okay, now this is a topic that I believe we discuss in the video on conjugation in the symmetric group, which is previously in this playlist on group theory, but I will just remind you of it here because it's an extremely important concept that we're going to use. Okay, so the best way to describe what is meant by the cycle decomposition of a permutation in the symmetric group on the set of n elements is just to do an example. So what I'll do is I'll take an example from the symmetric group on the set of 8 elements. So this is large enough that it won't be trivial, but not too large that it will just be hard work. Okay, so what I'm going to do is just make up some example of a set permutation from the symmetric group on the set of 8 elements. So here I'll draw out all of the 8 elements, so 1, 2, 3, 4, 5, 6, 7, 8, and then I'll have them again here, 1, 2, 3, 4, 5, 6, 7, 8, like so. And now let me just make up a set permutation. So I'm going to try and make this as wild as possible. 1 can go to 2, 2 can go to 1, 3 can go to 6 here, 4 can go to, where shall I have 4 going to? 4 can go to 3 up there, 5 can go down to 8, 6 can go to 2 right the way up there, okay, and then 7 can go to 5, and 8 can go to 7. So I've tried to make a really messy set permutation there, one that looks really complicated. And now what we're going to do is decompose it into its cycle decomposition and see actually how simple it can be made to look. Okay, how really the reason it looks so complicated is I've drawn it badly. Okay, so let's decompose it into its cycle decomposition, and of course I'm doing a concrete example here, but this works for an arbitrary set permutation in an arbitrary symmetric group on the set of n elements. It doesn't have to be S8. Okay, so the way you do this then is you start with number 1 up here and you ask where does that go. So you draw a curly bracket here and you put 1 as your starting point and you say 1 is going to go to 4, so I'll put 4 after it. So this is giving me the information that 1 goes to 4, and then what you're going to put to the right of 4 is where 4 is going to go. So 4 goes to 3, so 1 goes to 4, 4 goes to 3 here, and then what we're going to put next is where 3 goes, so 3 goes down to 6. Okay, so here is 6, and then where does 6 go? 6 goes up to 2, and where does 2 go? Well, of course 2 goes back to 1, so it will go back to the beginning here. So there's one of the cycles, and indeed it's a 5 cycle here. Okay, now what we do is we open a new bracket and start with the first or the lowest number that hasn't already been included, which is 5 in this case, so we'll start with 5 here. Where does 5 go? It goes to 8. Where does 8 go? It goes to 7, and then 7 goes back to 5, so we close the brackets there. Okay, so here is the cycle decomposition of this set permutation that you've got sitting in front of you here. And from this we would say that it's actually made up of a 5 cycle here, a cycle of 5 elements, and a 3 cycle here. Now, let me really now draw a picture to show you why the cycle decomposition is a useful concept. The cycle decomposition really explains to us how simple this element actually is, even though it looks so complicated. So how is this element simple? Does this element look so complicated if it's very, very simple, if it's built out of cyclic permutations that are so simple? Well, the reason is that I've drawn it badly. I've chosen to put these elements in a stupid order here. Okay, now of course you might look at this and think, well, you've actually put them in a really logical order. 1, 2, 3, 4, 5, 6, 7, 8, that's a very logical order. But of course you have to remember what this is really all about. This is much more basic than that order is. Okay, this is just a set of symbols. And we've defined a set permutation from the set of symbols to itself. Okay. The set of symbols could have been anything. Yes, I use the natural numbers because we like those symbols. But, they could have been whatever symbols you liked. And now I have put this set in an order here because my brain likes to put those elements in that order because these are the symbols that we use in the natural numbers, and the natural numbers does have an order defined on it. But in the context of this problem, these were just elements of a set and they didn't have an order defined on them. Okay, I've only put them in that order because I've used the same symbols for this set as I use for the natural numbers, the first 8 natural numbers. And over there, when we're dealing with the natural numbers, they do have a natural order. But in the context of this problem, I could have called these symbols whatever you liked. I could have made up stupid symbols, and then my brain wouldn't have had a preferred order to put them in. Okay, but that would have been just as much capturing this problem here of just having a set of symbols with a set permutation of it as this does with these symbols that I'm very familiar with. So what you have to understand is that this is not the right order to put those elements in. There is no right order to put those elements in because I haven't put an order on this set. I've put them in that order because my brain knows that those symbols are from the natural numbers, and over there in the natural numbers they have an order, but in this problem they don't have an order. So there is absolutely no need to put these symbols in that order, and this was a very bad order to put those symbols for describing this set permutation. A much better order to put those symbols in order to describe this set permutation would be like so. 1, 4, 3, 6, 2, and obviously I'm just reading it off here. 5, 8, 7. Okay, now I'll just copy it out here. 1, 4, 3, 6, 2, 5, 8, 7. Now let's understand why that's a much better order. Well, let's just copy the set permutation out now that I have rearranged the elements in this way. Okay, so where does 1 go? 1 goes to 4, so 4's now just below it. That's very nice. Okay, where does 4 go? 4 goes to 3. Oh yes, you might be starting to see why this is a good idea. Where does 3 go? 3 goes to 6. Excellent. 6 goes to 2. And then where does 2 go? 2 goes back to 1. Okay, and then where does 5 go? 5 goes to 8. Where does 8 go? 8 goes to 7. Where does 7 go? 7 goes up to 5. Bingo. Okay, this is the same set permutation, the absolutely same set permutation. I know it looks very different, but remember the set permutation is just this mapping from this set to this set. This is the same set as this. The set didn't have an order on it. I didn't define it to have an order on it. So just rearranging it like this on a piece of paper doesn't change the set in any way. And I haven't changed the mapping in any way. I've just displayed it in a different way to make it look simpler. And now, of course, it does look hugely simpler. I can see that actually this set permutation is just made up of a beautiful 5 cycle there and a 3 cycle. Okay, so if I want to understand this set permutation, this is obviously far more amenable to understand than that. Okay, so that's the use of decomposing elements into their cycle decompositions. It illustrates how, in fact, any set permutation is just built out of these very simple set permutations, which are cyclic set permutations. Okay, so there's a reminder of how to split a set permutation in the symmetric group on the set of n elements into its cycle decomposition. Okay, now that's just a little bit of a prerequisite, just a reminder of cycle decompositions. That's not really what I need to discuss. What I want to discuss, here comes the claim that I stated earlier on, but now I'll repeat it in more detail. So the claim that I need to discuss, and which is going to be really important for this entire video, is that if you take any set permutation from the symmetric group on the set of n elements, so let's call this arbitrary set permutation sigma, which is common notation. So sigma is going to be our arbitrary set permutation from the symmetric group on the set of n elements. The claim is that you can decompose sigma always into a series of successive transpositions. Okay, so I'll write the key words. Okay, it can be decomposed into a succession of transpositions. You can write sigma as one transposition followed by another transposition followed by another transposition, or maybe right isn't the right way to put it. You can build any set permutation out of lots of transpositions one after the other. Okay, by composing lots of transpositions together. Now, what's meant by a transposition? A transposition is a special type of set permutation where you just swap 2 elements. Okay, in the set of n elements, you swap 2 around and everything else remains fixed. So if I want to show you a transposition in the context of the symmetric group on the set of 8 elements, so let me just draw one out quickly. Okay, so I'll once again go back to ordering things like so. 1, 2, 3, 4, 5, 6, 7, 8, because my brain has an easier time remembering that. Okay, so this would be a transposition. We swap 1 and 3 around, but then fix everything else. Okay, like so. So 4, 5, 6, 7, and 8 are all sent onto themselves here. Okay, that is a set permutation on this set of 8 elements, and it is a transposition because it just swaps 2 elements around. It sends 1 to 3 and 3 to 1, but everything else is fixed. So that's what is meant by a transposition. So there are these special types of set permutations that will be in the symmetric group on the set of n elements that just swap 2 elements around. And the claim is that you can build any other set permutation in the symmetric group on the set of n elements by doing one transposition after another transposition after another transposition after another transposition, by a succession of transpositions, by composing them all together. Okay, so it's very simple to prove this, because we now know that any element can be decomposed into a cycle decomposition. Okay, so just to add another comment onto this, what I could view this element as is you could firstly do this 5 cycle, and then you could do this 3 cycle, and then overall that would build this. Okay, so let me just illustrate that with an actual picture of it. Okay, so 1, 4, 3, 6, 2, 5, 8, 7, and then I'll need this copied out twice more now. 1, 4, 3, 6, 2, 5, 8, 7, and I'll just make sure this is in view, yep. 1, 4, 3, 6, 2, 5, 8, 7. Okay, right, so this is the point that I want you to understand. I could build this element by firstly doing this 5 cycle and then doing this 3 cycle, like so. So here is the 5 cycle. 1 goes to 4, 4 goes to 3, 3 goes to 6, 6 goes to 2, and 2 goes to 1. But now we fix everything else. 5, 8, and 7 remain themselves. And then we do the 3 cycle, so where 5 goes to 8, 8 goes to 7, and 7 goes to 5 here. But then we fix all of the ones up here. 1 goes to 1, 4 goes to 4, 3 goes to 3, 6 goes to 6, and 2 goes to 2. Can you appreciate that if you worked out overall what that is equal to, what the 5 cycle composed with the 3 cycle is, you would get exactly this, and of course that's equal to this other thing in the silly order here. Okay, so I can actually view any element as do the 5 cycle, well, I can view this element as do the 5 cycle, then do the 3 cycle. More generally, if I've got an element, sigma here, which is in the symmetric group on the set of n elements, I can decompose it into its cycle decomposition, and I can view it as being built by doing 1 cycle, followed by another cycle, followed by another cycle, compose them all together, and the overall net result is the set permutation that I'm interested in. Okay, so that's another important point about cycle decompositions, that truly you can decompose your set permutation into do this cycle permutation, then do this cycle permutation, then do this one, etc. In this case, obviously, there's only 2 cycles in the cycle decomposition, but in other more general cases, there might be absolutely loads of them. Okay, right. So, if I can actually prove that any cycle permutation can be split into a series of transpositions, then of course for each of these cycles that makes up the entire set permutation, I'll be able to decompose that into transpositions, and then the entire element will decompose into transpositions because the entire element decomposes into cycle permutations. So in fact, to prove this, all I need to do is show you that any element, any cyclic permutation can be split into a series of transpositions. Okay, so to do this, I'm going to again do a concrete example and then go to the more general case. Okay, now I don't want to stick with S8 because S8 is a little bit big, so instead what I'll do is I'll go smaller. Let's go down to S4 to show this. Okay, so the symmetric group on the set of 4 elements now rather than the symmetric group on the set of 8 elements. So let's make a nice easy 4 cycle here. So we'll have, and I'll display it on its side this time since I've got a awkward piece of paper here. Okay, so 1, 2, 3, 4, 1, 2, 3, 4, and let's make a nice 4 cycle here that agrees with the order that I've put the elements in, that looks good with the order that the elements have been displayed in here. So here is a nice 4 cycle displayed here. What I want to show is that this 4 cycle can be decomposed into a series of transpositions, successive transpositions. Okay, so this is how I'll do it. So I'll start with the elements here, 1, 2, 3, 4, 1, 2, 3, 4. So what's the first transposition that I'm going to make? Well, in the overall thing, I want 1 to go to 2. So the first thing I'm going to do is to try and get 1 to go to the right place. So I will swap 1 and 2 like so. So I'll swap 1 and 2 around and leave 3 and 4 where they are. So they'll stay exactly the same. And from now on, I'm not going to move 2 at all. 2 must remain exactly on itself. Otherwise 1 will not go to 2 when I look at the net result. So I've made sure that 1 is going to the correct place now. Okay, with the next transposition, what I want to do is make sure that 2 goes to the right place. I'm just working along the elements here, one by one, and making sure they go to the right place. 2, unfortunately, at the moment is going to 1, so what I'm going to have to now do is swap around 1 and 3, because I want 2 overall to go to 3. So if I swap 1 and 3 around with my next transposition, like so, then hopefully you'll agree that overall now 2 is going to 3, and look, this is brilliant, 1 is still going to 2 because I've fixed 2 in this second transposition. Okay, excellent, so I've now got 1 and 2 going to the correct place. Now what I need to do is get 3 going to the correct place. So currently 3 unfortunately is going to 1, 3 needs to go to 4, so what I'm going to need to do is swap 1 and 4 around. So I'll send 1 to 4, and then 4 to 1, and I'll fix 2 and 3, like so. And look, bravo, now I claim that 3 is going to the right place, and now that means that 4 must be going to the right place because there's only one thing left over. Okay, if 1, 2 and 3 are all going to the right place, then there's only one final thing left over, and that must be the right place for 4 to go. So hopefully you appreciate that if I was to work out the net result of all of this, it would equal that 4 cycle here. So this 4 cycle has been decomposed into a succession of transpositions. Okay, now note how many transpositions it took. It took 3 transpositions. I had a transposition to make 1 go to the correct place, a transposition to make 2 go to the correct place, and a transposition to make 3 go to the correct place. But I didn't need a transposition to make 4 go to the correct place because that was the final thing. Okay, and its position will have been fixed after that. There's only one place it can go, and that must have been the right place for 4 to go. So it only required 3 transpositions, whereas if you've been asked to guess, if I'd been asked to guess before actually seeing this, I would have guessed you'd have needed 4 transpositions to make it correct, but you don't. You need 1 minus the size of the cycle to make it go correctly. Okay, more generally, if we've got the m cycle, 1, 2, all the way up to m, okay, we can do a very similar procedure to this. Firstly, we'll have a transposition to make sure 1 goes to 2, okay, then we'll have a transposition to make 2 go to the correct place, etc. And we'll work our way along the m cycle here, and we'll get to the m minus 1th thing here, and we'll have a transposition to make sure that goes to the correct place, but we won't need a transposition to make sure m goes to the correct place because there will only be one place for it to finally go. Okay, so overall it will require m minus 1 transpositions to build this thing, okay, in this way. So any cycle decomposition then, any cycle permutation can be built out of a succession of transpositions, and hopefully you now acknowledge that because any set permutation, any general set permutation sigma, can be decomposed into cycle permutations, and all cycle permutations can be built out of successive transpositions, the entire set permutation can be built out of cycle decomposition, out of transpositions, out of a succession of transpositions. So indeed the claim is true. Any set permutation can be built out of a succession of transpositions. Now, here comes the big topic that this entire video is now going to be about. The question is this decomposition into transpositions unique? Okay, is it unique? Is there only one decomposition into transpositions that you can do? Well, of course the answer is no. And let me give you a very simple example to show that. Let's take as our example a really simple set permutation, a set permutation that is a transposition itself. And again, it will be a set permutation in the symmetric group on the set of 4 elements. So it can be the transposition which swaps 1 and 3 around. Okay, like so. So of course, this is a set permutation in the symmetric group on the set of 4 elements, and of course it's already in its decomposition into transpositions because it itself is a transposition. So this is perfect. We've already got the decomposition into transpositions. It's staring at us already. What I'm going to show you is I can actually find you a different decomposition into transpositions of this, a different way to build it out of a succession of transpositions. So let me show you now. So again, 1, 2, 3, 4, 1, 2, 3, 4 here. So let's start by swapping 1 and 4 around, like so, and keeping 2 and 3 the same. Okay, now let me start fixing this. I just made this up as a silly one to put in there, but now let's try and fix it so that it's actually going to make this overall. So we want 1 to go to 3. At the moment 1's going to 4, so we better swap 3 and 4 around. Okay, so let's do that. So I'll swap 3 and 4 around like so, and then obviously I'll have to keep 1 and 2 the same. So now 1's overall going to 3, 2's going to 2, that's excellent. So which ones are wrong? 4's going to 1, that's obviously wrong, and 3 is going to 4, that's obviously wrong. So now I think all we need to do is swap 1 and 4 around. So I think if we send 1 to 4 and 4 to 1 like so, and fix 2 and 3, that should do the job. So 1 will now go to 3, excellent. 2 is still going to 2, that's excellent. 3, where's 3 going? 3 is going to 1, that's excellent. And 4 is staying at 4 overall. Okay, so there is another way of building the same set permutation out of transpositions. Okay, so certainly it is not true then that any set permutation in the symmetric group on the set of n elements is going to have a unique decomposition into transpositions. Absolutely not true. Okay, there are loads of different ways of building each set permutation out of transpositions. So this is looking rather hopeless. There is, however, a claim that we can make. There is something we can always say is true. And let me just point it out here. I had one transposition here. This was one decomposition into transpositions to build this element. Here was another decomposition into transpositions to build this element, and overall it took 3 transpositions to make this. The claim is that for any set permutation here, okay, any set permutation in the symmetric group on the set of n elements, if you produce a decomposition into transpositions, the parity of it will always remain the same. Although, you know, there may be loads of different decompositions into transpositions which you can use to build this element, the parity of all those different decompositions is the same. Okay, and if you don't know what parity means, I'll explain in a moment. The parity remains the same. Okay, so parity is a fancy word meaning whether it's odd or even. Okay, that's what it means. Parity means is the number of transpositions, in this case it refers to the number of transpositions that you have to use to build it, is the number of transpositions that you've got here odd or even. Okay, and you'll note here that both of these decompositions into transpositions were both odd. Okay, I claim that if you wanted to build this element by any decomposition into transpositions, you would never, ever be able to find one that contained an even number of transpositions. Okay, have a go, have a challenge. Okay, try and find a decomposition into transpositions of this element in the way that I've just done. Okay, find other ones. Try and find one that has an even number of transpositions. You will fail. Okay, the parity of any decomposition into transpositions for a certain element remains the same. Okay, now both of the elements that we've actually done in this case, so this one here, this 4 cycle here, it was also an odd, it had an odd number here. It had 3 transpositions that was needed to build it. Okay, if you took any other decomposition into transpositions, the number would also be odd. However, there are set permutations where the number would be even. So every single set permutation in the symmetric group on the set of n elements can be called either even or odd. And this is going to be the sign of that set permutation. We'll give it the number +1 if it's an even one, and we'll give it the number -1 if it's an odd one. Okay, so that's what the sign of a set permutation is going to be. It's going to be, if you decompose it into a series of transpositions, is the number that you end up with always going to be odd or always going to be even? And that is something that will never change. Okay, so this set permutation is an odd set permutation. This one is also an odd set permutation in the symmetric group on the set of 4 elements. Find any decompositions into transpositions you like of these set permutations. You will never ever find one that has an even number of transpositions. Okay, so we'll have a break here, and in the next video what we'll do is try and prove this great claim that the parity remains the same, because obviously it does require proof.